Okay, we're going to move on to 4.2, which is characteristics of polynomial functions. Characteristics of polynomials have to be, first of all, continuous. That means that they go on forever in both directions, and they have to be smooth. So this is a polynomial function because it does go on forever. And we're assuming it's going on forever in both directions. They don't have arrows there, but we're just assuming they are. This is not continuous because there are breaks in it. So it started here, ended there, then it started a whole nother part and ended there. So this is not a polynomial. They have to be smooth, like a roller coaster ride. You don't want a roller coaster ride that's going to be like this absolute value function and you crash right here and die. So it has to be smooth with rounded corners. So this is a polynomial function. This is not. Another example of polynomial functions is that when you write them in general form, like our quadratic, so this is our quadratic, and we talked about this being in general form, our exponents are in decreasing order. So this is x to the second, this is x to the first, this is x to the 0 power. Anything to the 0 power is 1. So all of this is in decreasing order from your exponents. So that's what this is saying. So our polynomial functions are going to be in decreasing order, where our exponents are whole numbers. Oopsie, not humbers, numbers. This is a whole number. This is a whole number. That's a whole number. Whole numbers are our set of numbers from 0 and increasing by 1. So we want our exponents to be whole numbers, not fractions. So determining a degree in a leading coefficient. So I've talked about this also. Once we get this in increasing or decreasing order, then this very first term that we have right here, is our leading term. This coefficient right here that's attached to that x value, that's our leading coefficient. And then this exponent right here, that is the degree of our polynomial. That's the highest degree, I should say highest. We eventually stop saying the highest degree and we just say, what is the degree of the polynomial? And you know that's going to mean the highest degree. So this term right here is our constant term, if there is one. Sometimes we don't have a constant term. Constant meaning just a number. Okay, so we're going to look at these examples and we're going to say what the leading term is, the leading coefficient, and the degree. So first of all, when I look at this, I have to see if it is in descending order by its exponents. So I'm going to look at my exponents. This is x to the first. Here's my constant term, so that's x to the 0. This is in decreasing order. Once I have that, I know that, oopsie, here's my degree, here's my leading coefficient, and that's my leading term. So I don't even look at any of the other stuff. You can tell a whole bunch about a function just by looking at its leading term. So we're going to write down what all of those parts are. So we have our leading term. I'm going to write LT for leading term is 5x to the 6th power. My leading coefficient is 5, and my degree is 6. Another thing that we call degree is n. So let's look at this second example. I have to look and see if it's in descending order by my exponents, and it's not. So maybe I need to rewrite it. I will rewrite it. This is my leading term. You cannot forget that negative there. And then x2, 2x squared, and then 7x, and then 3. So here's my leading term. This is my highest degree, or my degree, or n. And then I have my leading coefficient right there. So my leading term is negative 4x cubed. My leading coefficient is negative 4. And my highest degree, n, is 3. So let's look at the third example. The third example, I see that I am in descending order right here. So that's pretty easy. Here's my leading coefficient. Here's n. And here is my leading term. So the leading term is 5t to the 5th power. My leading coefficient is 5. And my degree is 5. So now let's look at the fourth one. The fourth one is not in order, so let's rewrite it. I have negative p to the 3rd power plus 6p minus 2, which tells me that I have a leading term of negative p to the 3rd power. That negative is attached to a 1 that we never ever write, but I need to know what that is for my leading coefficient. So my leading term is negative p to the 3rd power. My leading coefficient is negative 1, and n equals 3. Okay. Any questions about that? So now let's look at the next heading. It says number of x-intercepts and turning points. So we just talked about turning points, and previously we've talked about x-intercepts. And I have tied all this together and talked about it already before, except the turning point. So let's scoot on up here where I already talked about turning points. Let's use this one, for example. This is a turning point because I'm changing from increasing to decreasing. This is a turning point. This is a turning point. So I have 3 turning points. The one above it, I have 1, 2 turning points. the one above that, I have 3 turning points. So those turning points are related to what we just talked about with our leading term in our degree in our leading coefficient. So here we are. We know that the x-intercepts, that's where this is crossing the x-axis. I can find that, and I've said this about quadratics and our other polynomials that we've worked with, by looking at the highest exponent value. So n is going to be how many x-intercepts we could possibly have. We don't have to have that many. So we could have at most n x-intercepts. Where n is the highest degree. So let's remember our quadratics and say why this says, and see why this says at most. So with our quadratics, we had that situation, we had that situation, and we had that situation. Our quadratic is to the second power. That's my highest degree. So I have 2 x-intercepts here. Here I only have 1, and here I have 0. So at most, this tells you how many you could possibly have, but you could have less. I could have 1 or I could have 0 of quadratics. Turning points means at most you're going to have n minus 1 turning points. Again, where n is the highest degree. Oopsie. Okay, so let's look at this example. This is a 4th degree polynomial. I see that because I see that my highest exponent value is 4. So we call it a 4th degree polynomial. So my x-intercepts could at most be 4. And I see that they are because I have a graph of that. But if I didn't have a graph and I just had this equation, I would know that I could possibly have x-intercepts. 4 x-intercepts. At most 4 x-intercepts. But I see that I do have 4 on this graph. So now let's look at turning points. Turning point says that I could have at most, what is n? 4. So I'm going to plug it in there. 4 minus 1 turning points. And let's go ahead and finish that. 4 minus 1 equals 3 turning points. Well, let's look at the turning points and see if I have 3. Here's 1, here's 2, there's 3. I do. So I have exactly 4 x-intercepts and I have 3 turning points. Another way that you could look at turning points is how many times are you changing from increasing to decreasing. So that's 1 time, 2 times, 3 times, if you have a graph to look at. Okay, so here's an example without graphing the function. So we have just this function, and we want to determine the local behavior of the function by finding the maximum number of x-intercepts and turning points. So I'm going to write x-intercepts, and I'm going to write turning points. First of all, is this in descending order? Yes, it is. So I see that n equals 9. So I can have at most 9 x-intercepts. That means I could have less than that. I could have 8, I could have 7, I could have 6, I could have 5, 4, 3, 2. Turning points is going to be at most 9 minus 1, which equals 8 turning points. Let's do the next example. So our next example is not in descending order. I'm going to look at my exponents, and I see that this is my highest exponent value. So I'm going to put a box around it, and I know that n has to equal 12. So I know that I'm going to have at most 12 x-intercepts. And I'm going to have at most 12 minus 1, which equals 11 turning points. Does anyone have any questions about that? Okay, so we have to keep all of that in our head, and we're going to move on to some more stuff with our, what's it called? No, I forgot. Leading term, sorry. I'm going to remind you that it's a times x to the nth power. So whatever this is and whatever this is, if that's our leading term, then n is our highest degree. This is my leading coefficient, and that comes from our leading term. So we're going to look at characteristics of power functions. Power functions. This is our power right here. This is our power. So that power, I told you, had to be an even number. I mean, not even, had to be a whole number. So our whole numbers, let me just list them out. We have 0, 1, 2, 3, 4, 5, 6, and so forth and so on. Right here, I'm underlining even numbers. That looks like the same color. Here are odd numbers. So our power is either going to be even or odd. So we know what's going to happen with polynomials because of that power. If n is even, which we're going to associate it with our parent function of a quadratic, then I know that both of the end results are going to end in the same direction. So end results meaning this is going up, that's going up. 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 The end results are going in the same direction. So as n increases, n meaning the power, So I have n to the second power, n is the 4, n is 6, n is 8. So as n is increasing, look what's happening. This is x squared. This is x to the 4th. This is x to the 6th. And this is x to the 8th. So notice that it's pointier on x to the second power, but on to the 8th power, it's getting flatter. So as n increases, the graph gets flatter around the origin, but increases faster. So right here, let's look at this purple one. So I have a smaller interval along my x-axis, so it means that the interval is getting smaller between those parts. I'm just going to write that. The graph gets flatter. So over here, let's also look at for even powers, the graph has the same end result. Now let's look at odd. So let's look at our parent function x to the third power. So x to the third power is this one. This is x to the 5th power. And then I have x to the 7th power. And then x to the, it's right here, x to the 9th power. So the same thing is happening down here. As n increases, so here's 3, here's 9. Notice how the red one or the black one is not as flat as this green one. This green one gets flatter. So the same thing happens. But also notice that I do not end up in the same part. Here I'm going down, here I'm going up. All of this was up and up. So for odd powers, the graph has opposite end results. This is down, that's up. Those are opposite. Okay, so let's look at our leading coefficient test. So remember our leading coefficient for a x to the nth power was my coefficient, yellow. This is my leading coefficient. So this number right here can either be positive or negative. So A is positive or A is negative. So I have two possibilities. This is positive or negative. So if I have a positive coefficient and I have a negative coefficient, what's this doing to my odd function? So when n is odd. So let's draw a picture of it. I'm going to draw something similar to x to the third power because that's what this says to do. So when n is odd and I have a positive coefficient, it's going to look like the slope of a line. So it's going to start low and it's going to go high. And remember, we said when I have an odd power, then I'm going to have different end results. So now let's look at what happens when I have a negative coefficient. So it's going to have the slope of a negative line. So negative goes from high to low. So it might look like this. So now let's talk about what's happening with this function. So as I'm moving from along the x-axis from left to right, as x approaches negative infinity, well, let's go this way. As I'm going to negative infinity this way, then f of x is going to negative infinity. That means the y's are going down. Let's do the same thing on this part right here. As I'm going to positive infinity, then my f of x or my y values are also going to positive infinity. So now let's look at this one. As x approaches negative infinity, so as I'm going to negative infinity, my f of x is going to positive infinity. And then on this side, as x is approaching positive infinity, my x value is moving this way, then my f of x is going to negative infinity. That did not work so great. That did not work so great either. That's a negative. Okay. So now let's look at this next example. I have a positive coefficient, so that means A is positive, and N is going to be even. So we're making sure it's even right here because I'm multiplying N by 2. If you multiply any number in the whole world by 2, it makes it an even number. So they're saying that our highest degree is even. And A is going to be positive. So when A is positive, we're going to think of our quadratic. In our quadratic, we were happy. It's going to end like this. So it could, if it's not a quadratic, it could be something else. It could look like this. And that's fine. I know that this is an even exponent, and it has a positive coefficient because positive is happy. It's making a smiley face right here. So if my coefficient is negative, it has to end in the same result. That's what I would have. So I only have 4 possibilities of what our polynomial functions can look like. There's only 4, and they're all based on this leading coefficient and this exponent. So let's look at our notation here. So as x approaches negative infinity, f of x is going to positive infinity that direction. And then here, as I'm going to positive infinity on my x-axis, f of x is also going to positive infinity. So let's look at our last one. As x approaches negative infinity, so I'm going to the negative infinity part, f of x is also going to negative infinity. And here, as x is approaching positive infinity, f of x is going to approach negative infinity. Okay. So remember that our graphs don't have to look like this in the middle. I mean, I could take that away and I see that I have a positive coefficient with an odd exponent. That's what the end result's going to look like. Here I have a negative coefficient with a odd exponent, and this is what our end result's going to look like. Here I have a positive coefficient with an even exponent. It's going to look like this. And then I have a negative coefficient with an even exponent. It's going to look like this, the end results. So now let's look at some examples. I have f of x equals negative x cubed plus 4x. So the very first thing I'm going to do is what I previously did. Make sure this is in descending order. Identify my leading term. So this is telling me that my leading coefficient is -1 and my highest exponent value is 3. So my coefficient is -1. That's odd. N equals 3. That is, what am I doing? That's not right. Sorry. This is negative. 3 is odd. So I'll look up here at this graph. Here's odd, where n is odd. And if I have a negative coefficient, I know it's going to look like this. So my graph of this equation is going to look like this. My end result. There's going to be some stuff happening in the middle, but I'm just going to care about the end results right now. So I know as x approaches negative infinity, this direction, then f of x is going to positive infinity. And as x approaches positive infinity, so that means moving this way, f of x is going to negative infinity. So I just wrote down this stuff right here. Now let's look at this example. This example is in descending order, so I know that's my leading term. From that, I see that my leading coefficient is 2, and my highest exponent value is 4. So this leading coefficient is positive, and my highest exponent value is even. So let's look at our positive, even. So here's even, here's positive. It looks like a quadratic on the end results. So it's going to look like this. There's going to be some stuff going on right here, but I don't care about that right now. I'm just going to care about the end result. So as x approaches negative infinity, you can look up in your picture and write this down, but I'm just going to say it over again. As it goes to negative infinity, then f of x is going to positive infinity. As x is going to positive infinity here, then f of x is going to go also to positive infinity. Now let's look at number 3. We're going to make sure that we know what our leading term is. I have a 4 as my exponent, a 2, a 1, and a 6. So this is my leading term right here. I'm not going to rewrite the equation. I'm just going to put a box around it because all I need to know is my leading coefficient is negative 1/2 and my highest exponent value is 6. This is negative and this is even. So looking at my picture for even and negative, I know that both parts of the end results are going down. So here's my coordinate plane. It's going to look like this. So as x approaches negative infinity, that means moving this direction, then f of x going in the y direction is also going to negative infinity. As x approaches infinity this way, f of x is going to negative infinity. So they both have the same result. So when I said even numbers have the same end result, where are they ending? These are both ending in a positive direction. Positive infinity. These are both ending in negative infinity. This one is odd. So odd is going to be opposite. The end result is going to have opposite parts here. Here's a positive infinity and a negative infinity. Okay, so now we're going to put the whole picture together. We're going to talk about all the stuff. So I have this example, and it says, given the graph of the polynomial function, determine the least possible degree. So we've talked about the degree of our polynomial, that's n. So I want to know what could n be of the polynomial and whether it's odd or even. So I only have 4 possibilities for what a graph can look like. And I see that both of them are going up. So when I go back to this picture, I know that it has to have a positive coefficient and n is even. That's what this is. N has to be even. So I'm going to write that down. N is even because the end result is the same. Oopsie. Right here. So now I'm going to ride the roller coaster, and I'm going to remember that we did that and we found our turning points. So I have this turning point, I have this turning point, and I have this turning point. So I have turning points are 3. How did I get turning points? So we scroll back up here. To get our turning points, we did n, the degree, minus 1. So I already know what the turning point is. So I know I can put an n minus 1 here and know it has to equal 3. So I just add 1 on both sides and I get n equals 4. That is my degree of this polynomial. And that makes sense because let's scroll back up to the very beginning. Where is that at? Of this section. With our power functions, here's x to the 4th power. Right there. Okay, so now let's look at number 2. Number 2 says, given the following functions, I have 2 of them, determine the end behavior, the maximum number of real zeros, the maximum number of turning points, and the x and y intercepts. All right. So let's identify our leading coefficient, our leading term. This is our leading term because this is in decreasing order. So my leading term is 2x to the 3rd power, and I know that my leading coefficient is 2, and I know that n is 3. So now we know some stuff about our leading coefficient and our highest exponent value. This leading coefficient is positive, and this highest exponent value is odd. So a positive odd function is going to look like this. N is odd, and the leading coefficient is positive. I lost my picture. There we go. So I know it's going to have opposite end results, something like that. I'm just going to put that there to remind me what it is. I know also that I can find the y-intercept just like I did in every other polynomial function with lines or quadratics or anything. I can set y equal to 0. That means f of x is going to equal 0. No, I did that wrong. Sorry. I'm going to set x equal to 0 to find my y-intercepts. So normally when it's in general form, if I had a constant term here, this would be my y-intercept. But I don't have one there that we write down. It's going to be 0 because I'm going to plug in a 0 for all of these x's, and it's going to tell me that this equals 0. So let's do that. F of 0 equals 2 times 0 cubed minus 6 times 0 squared minus 20 times 0. All of that equals 0. So here's my input of 0 and my output of 0. So I know that is a point on the graph. Now I'm going to do x-intercepts. So to find the x-intercepts, I'm going to set f of x equal to 0. So this is going to be set equal to 0. So I have a greatest common factor. I have a 2 and x. That's my greatest common factor. 2x times x squared is 2x to the 3rd power. 2 times 3 is going to be, or negative 3 is negative 6. And x times x is x squared. 2 times negative 10 is negative 20, and I factored out the x. So now I can factor this quadratic. I need factors of -10 that add together to be -3. That's going to be -5 and +2. So now I'm going to take all three of these parts and set them equal to 0. So I have 2x equals 0. I have x minus 5 equals 0. And, oopsie, x plus 2 equals 0. So when I divide both sides by 2, I see x equals 0, which we already knew that right there. I add 5 on both sides, and I get x equals 5. 1, 2, 3, 4, 5. And I subtract 2 on both sides, and I get x equals -2. So I know that my graph is going to look something like this. Probably not all the way over there. It'll go here. Then it has to come back down. Oopsie. Oopsie. Not doing great. And then it has to go back up. So it's going to look something like that. These turning points are going to be different. We don't know how to find the turning points right now. So we're just going to leave it like that. Let's see if we answered all of our questions. So the maximum number of real zeros, that's my highest exponent value, which is n. The maximum number of turning points is going to be n minus 1, which is 2. And there they are. And I found the x and y intercepts. So now we're going to do the same thing with this last example. So this is in descending order, so I know this is my leading term. So my leading coefficient is 1, which is positive. And then my highest exponent value is 4, and that is even. So positive and even, it's going to look like a quadratic, kind of, with our end results. So I know that this is my maximum number of zeros that I can have is 4. Let me write this down because I didn't on the last one. Maximum number of zeros, that's the same thing as maximum number of x-intercepts, is 4. And my turning points is going to be 4 minus 1, which is 3. So that is this and this. Now I'm going to do my x and y intercepts. So to find the y-intercept, x equals 0. So I'm going to take this equation and I'm going to show you again that I know that's going to be my y-intercept. I'm going to plug a 0 in for x. This is 0, that's 0. So this is going to be -45. So if I count by 5s, 5, 10, 15, 20, 25, 30. Nope. If I count by 10, 10, 20, 30, 40, 50, -45. If I count by tens, is right there. So I have 0, -45. Now to get my x-intercepts, I got to set the function equal to 0. So I'm going to take this function, set it equal to 0. So this is a quadratic type. Remember we talked about this and this was on your exam. If this number cut in half is this number, then I can solve this like a quadratic. I'm going to try to factor it. X squared times x squared is x to the fourth. I need factors of negative 45 that are going to add together to be negative 4. So that's going to be negative 9 and positive 5. So now I'm going to scoot up here and set it equal to 0, each part. So if x squared minus 9 equals 0, and x squared plus 5 equals 0. So we're using the zero product property to set both of these factors of this fourth degree polynomial equal to 0. So I'm going to move this over because I know I can take the square root of both sides if I don't have a x to the first power term. And I get x equals plus or minus 3. So 1, 2, 3. 1, 2, 3. And then here, I'm going to move the negative 5 over. I'm going to take the square root of both sides, and I get x equals, this is a negative under the square root, so I can write this as the square root of 5 times the square root of negative 1, and the square root of negative 1 equals I. So this is I. So this is going to be the square plus or minus the square root of 5I. So those are imaginary solutions. So I don't have 4 x-intercepts like this tells me that I could have. I don't. I only have 2 real solutions. I have 2 imaginary solutions. So my graph is going to look something like this. It's going to be not doing great here. It goes through here and gets fatter and then goes back up. Pretend that's beautiful. It's not, but pretend it is. Okay. Let's see if we answered the questions. I did x and y intercepts. I did maximum number of turning points, and I did the maximum number of real zeros. So that is where we're ending for this week. We did 4-1 and 4-2, and we'll do 4-3 after spring break. So did anyone have a question?